So in the last video, we worked out all these quantities you see here on the right. And what we're really motivated to try and do here is find V cross L. The true motivation of what we're trying to do is find a relationship between R and theta. And given that the angular momentum L is constant, we might have a shot at doing that if we sort of play our cards right, if we can do the mathematics correctly. And really, it's just logical deduction is what it is. So we're trying to find V cross L, and I told you we're gonna get A cross L first. It doesn't make sense, but right now we're gonna get A cross L first. It is going to become apparent soon why this helps us. We then developed the vector V in polar coordinates, and then we figured out that the time derivative of R hat is equal to this quantity. This will be useful in a minute. And we defined our inverse square law in terms of these this vector system that we've created with our hat, theta hat. And the inverse square law was something that sort of started off this whole video series and actually derived it in the first video. Okay, so let's try to compute this thing, and let's rewrite it out over here. So it's going to be m, and we're gonna do some things here. We're going to do some things. We see this A. We see this A. This vector A is in both places, and basically there's some constants here in front of A that we can actually take out, and doesn't affect the dot products at all. So we're going to take out the negative GM over R squared. I'm going to take those out. I'm going to give myself a nice big bracket here. And then we need to sort of try to compute all of these dot products. So what's left, once you take all that out, you just get R hat. I'm going to dot that with V, and then multiply that by R. And let's rewrite R as, well, R is simple, R is R hat. And then subtract. Once again, there's only R hat left once you pull out all those constants from that A, dotted with the vector R, which once again is just R hat. And then all multiplied by V. Okay, so let's use white. So these constants are still there, gm little m over R squared. And then, well, what is R hat dotted with the vector V? All it really is just a component of V in the R hat direction. Okay, so what we're left with here is just R dot R and then R hat. All right, and then here, this one is really obvious. It's R hat times R times R hat, which is literally just R. Because it's this R hat vector, what component is in the R hat direction? Well, it's R. It seems like a really convoluted way to say that. Let's write V as a column vector here. Write V as a column vector. We know it has two components. We've written them out. It's R dot and then R theta dot. Okay. And then we can rewrite the one on the left as a sort of column vector as well. You get GMM over R squared, and then use a round bracket. So this one is just going to be R dot R, and then 0 minus, and then let's bring the R inside. We get R dot R again, and then R squared theta dot. Okay, so now this is just two vectors. We can do vector subtraction here. So you get negative GM m over R squared, and then a vector quantity. So the top actually cancels and becomes 0. The bottom becomes minus R squared theta dot. Okay, now we can rewrite this because this negative and negative becomes a plus, and then let's use orange. This becomes GM m over R squared times R squared times theta dot in the theta hat direction. Okay, so we see our R squareds canceled. That's nice. What we also notice is that theta dot theta hat happens to be equal to d by dt of r hat. And it's no coincidence that I sort of laid all of these nice definitions out here for us to see them. Now, remember what it was that we just calculated. We just calculated this whole thing was A cross L. So let's not forget that. All right, so we've deduced, let's see if I can fit that on the screen here. We've deduced that A cross L is equal to GMM times d by dt on r hat. Well, a couple things we can do here. We can rewrite A as d by dt on v, and then that's sort of cross L. And then let's bring the constants inside the differentiation, which seems bizarre, but it'll just sort of help us visualize it. Okay, so we can kind of see, we can actually pull this d by dt out on the left here, d by dt of v cross L. So it may be dawning on you why we've done all of this sort of complicated stuff. And the reason is, give myself a little bit of room here, is that we've now created a quantity that we can integrate very readily, actually. So if we integrate both sides, we're going to get rid of the dt's. We're going to integrate both sides. This is an indefinite integral, and we're going to include our constant of integration on the right. So this indefinite integral becomes v cross L. V cross L is equal to g m m in the r hat direction plus some arbitrary vector we're going to call d. I think d is the standard way to write this. And we have to make one sort of further argument, and this is one that I don't fully understand where it comes from, but it is, you might call it a postulate. It's an assumption, is what it is. And it's, well, we know we have the vector r, which is at some angle theta to the plane. And what I'm telling you, sorry, that wasn't very straight. What I'm going to tell you is that there's a vector r, or d, sorry, there's a vector d that lies in this plane such that it makes an angle theta with r. And the reason I tell you all this is because we're trying to calculate this. This was the very first thing we set out to calculate, actually. And so now we need to do that. We need to do m times, let's use white, m times r dotted with that quantity. Now let's write that out and make sure it's very clear. R dotted with g m m r hat plus this arbitrary vector d, and this all equals L squared. Okay, so what I'm going to say is that d makes an angle theta with r and can be projected down onto r. Okay, so we know what r is. Let's remind ourselves r is equal to r times r hat. So when we multiply this through, going to get g m m r. Okay, so that's the first vector quantity. And the second vector quantity, let's do it in blue, is going to be r, so r multiplies through still, and then d cosine theta. Okay, so what we can do here is we can just start to sort of rearrange stuff. And I'm going to bring the m over right away just to help us out there. And we can kind of separate, r, going to get, I think we need to divide r outside of GMM plus, yes, I'm sort of starting to recall this. We leave the GMM outside, and then we take this vector, sorry, this 1 plus, and then we take our vector d and we divide it by GMM in order to sort of make that equal again, and times cos theta. Okay, so this is L squared over M. It's just a bit of sort of algebraic manipulation. All right, so we're obviously getting very close here. We're going to divide both sides by m, so this m is gone, and we pick up a square here. And what we get is r on this side. On the other side, we get L squared over M squared, all over GM outside of 1 plus D, let's do a different color, D over GM, M, little m, times cos theta, times cos theta. All right, so if you watched the a couple videos back when we did the video on ellipses, you'll notice that this is of the exact same form. Okay, this is the exact same form. And the only other thing you need to note is that the eccentricity, E, is going to be equal to D over G, capital M, little m. And maybe it seems like an anticlimactic finish, but this is it. This is the result. I showed in a previous video that when r depends on theta in this way, and for a standard ellipse, let's see if I can get this right. I think it's just a outside of 1 minus epsilon squared over 1 plus r cos theta. Sorry, 1 epsilon cos theta. We can see that we have this form. All right, this GM on the bottom here you can bring up top. It's just a constant, and we have this exact form when we allow epsilon to equal d over GM little m. So I'm kind of putting my pen down now and just kind of staring and looking, sitting back and looking at this. But this is the result. This is, like I said, maybe anticlimactic, but there's a lot that went into this. There's a lot of sort of rigorous ideas that have to go into this process in order to obtain this result. It is a fascinating thing to go through as an exercise and realize what might have been going on in the minds of some of these geniuses from sort of the 1600s, 1700s, and how they thought about the world and what they thought about the world when they looked up at the stars and wondered about, you know, how planets move and how galaxies form and some of these really great questions. So so that's it. This is how we get elliptical orbits in Newtonian mechanics from the inverse square law. So thanks for watching. This kind of concludes my series on what I called the beauty of physical argument. And I don't want to talk too much philosophically about this, but I think it's beautiful. I do think it's beautiful that you can take these ideas, these thoughts, and use mathematics to describe them and come up with a result that is verifiable with experiment to a very high degree. I mean, it was the early 1900s before we were able to sort out some of the small errors with some of these orbits due to relativity. So I think that's just a fascinating concept. Thanks for watching as always, and if you liked it, please subscribe and leave a comment, and I will see you next time.